there. And the injector, you see, has a large external surface. And what will you do? You will vaporize the fuel inside this tube, inside this injector. You will say me, but why are they not always doing something like that? Because it's an injector that can only work when you have a temperature of the air that is high. So this is an injector that can only work when you have already started the engine. This is not an injector that you can use to start the engine, so from scratch. This is an injector that needs one of these two injectors to start the engine, and then this one can take the role of the main injector. So you would have then a start injector of this type, a start injector of this type, and a, let's say, cruise injector like the vaporizing injector that we are discussing here. And these injectors are also a very important part of the question, and we will discuss them with more details when we are discussing about the ways exactly these pressure swirl atomizers, for example, are used. Okay? And so you see like this the contributors, the different subcomponents that we have in this combustion chamber. Two tubes, an external one that is closed, an internal one that is full of holes. You have an injector. In the full of holes, you have holes that are going into this direction, going to this direction, going to this direction. And here at the exit, you can have a fully mixed flow or an unmixed flow or a not fully mixed one. And you have globally divergent, convergent. Okay? So like this, you have a very clear idea. And it can be tubular, it can be annular, it will have still the shape that we see here. We have here a divergent, and we see here the very large convergent. So you see, let's say very large convergent, very small convergent. So you see that we are really decreasing a lot the height of the combustion chamber in order to increase the speed a lot at the exit. Okay? So very interesting to see the global architecture of this combustion chamber. Okay? Now, what do we need also to discuss related to combustion chambers? We need to discuss what are the parameters. What are the parameters of a combustion chamber? At the moment, we know two parameters. The two parameters we know, this is eta Cc, the combustion chamber efficiency, and lambda Cc, which is the combustion chamber total pressure loss. In fact, there are other parameters that we need also to discuss. One of them is sometimes called the pattern factor. This is, let's say, the temperature profile that you are creating through the combustion chamber. So the fact that at the exit you want to have a certain temperature profile. I will come back on that in a minute. Another parameter that is quite important, this is what is called the intensity, or that you could call also the compactness of the combustion chamber. So this parameter is a very, let's say, specific parameter of gas turbine engine combustion chambers, which is in fact defined as the mass flow rate of fuel multiplied by QCI. So this is the amount of calories that you are injecting inside the combustion chamber, divided by the volume of the combustion chamber, and divided by the total pressure that you have in the combustion chamber. You see that it's something that is in watt. Normally, it's expressed in megawatt, because m.f, it is 1.5, 2 kilo per second. So we are speaking about huge power huge powers that are injected inside the combustion chamber in cubic meter bar. So very strange unit. And this is extremely important because I mentioned to you that I want to have this small. So I want to have this high. And the higher this intensity of the combustion chamber, the higher, in fact, the quality of the combustion chamber for an aero engine. You can have values as 60, 70, 80 megawatt per cubic meter bar. Whereas in an industrial gas turbine, you will be maybe at 10 only. Why? This is because if you increase it by, let's say, 5, that means that you have a much more compact system and that you have a small volume occupied by this combustion chamber. So, and this is, of course, this VCC related to the length of the combustion chamber, and let's say this A2 prime that you have here and this A3 prime that you have there, and maybe a small divergent and a small convergent at the back, but this is mainly equal to the cross-section, where the section is constant multiplied by the length of the combustion chamber, and so that means mainly that this is decreasing. The length of the combustion chamber is decreasing. If the length of the combustion chamber is decreasing, that means that if you take the compressor and if you take the turbine, so the compressor and the turbine, so that means that you will have a small, let's say, distance in between, and so this is clearly related with LCC. So if you increase this, you decrease this, you decrease this, you decrease the distance between the compressor and the turbine. The compressor is most probably much larger than that. And why are you doing this? In order to be able to increase the rotational speed. And we know that the rotational speed is a very important parameter. So this is more, let's say, a kind of quality parameter related to the compactness than related with the working condition of the combustion chamber. Another parameter that is extremely strange, this is this parameter. I discussed that already with you by saying that you can have maybe a part of the air that is not mixed directly with the exhaust gases here. Meaning that this is the radial direction, that at the root of the blades that are following here, you have a lower temperature than a bit later, a bit further in the radial direction, and again a lower temperature here. So don't forget that you have something that is like this. So I'm trying to explain you. So you have something that is like this. So behind the combustion chamber, you have the turbine blades that are just in front. Of course, this is not the same engine as this one, but you can understand what I was trying to show. And what will be the type of, so you have, so the shaft of the engine is here, you have the disc of the turbine that is here, you have the blade that is here, you have the external skin that is there, and you have the combustion chamber is here. Maybe with a double wall still at the exit. And what will we have? Normally, we will restrict the temperature of the gases at the root of the blade. Why? This is the place where the centrifugal stresses are the largest. So you have very large stresses there. Also in this place you have concentration of stresses, because you have the blade that is inserted inside the disk as you can see here. So you have concentration of stresses that you see, so due to the shape of the blades and the shape of the disk and the, let's say, insertion that you have in between. And also you can have there, let's say, strange shapes where, so you have, let's say, corners, and where you could have also large temperature gradients that are very bad also for thermal stresses. So large stresses here at the root, at the hub of the blade. And at the tip, you have also problems. Why? Because in a rotating blade, the cooling air is coming from the center. So the cooling air is coming from there, inside the blade. And so the cooling air, that we will discuss later on, sees the temperature of this cooling air increasing in this direction. So the air is hotter and hotter and hotter. So it's less well cooling the tip of the blade. The tip of the blade is less cooled, less efficiently cooled than the center. Also, this is a free edge. And there also, everything is rotating. If you have particles, they will be centrifugated, and this is where you have the largest danger of erosion. That's why here, due to the very high stresses, and here due to the less cooled blade, so the temperature of the metal at the tip is higher than the temperature of the metal at the root. This is what I mean. Here the temperature of the metal is larger than there, and due to the danger of erosion, what will we create as a profile? We will create a profile like this one. So it's not starting from zero. So this is maybe, I don't know, starting from 800 Celsius, 800 Celsius here, and here, so this is 800, starting from zero, and here, so it's not starting from zero, it's interrupted, and here maybe we have 1000 Celsius in the middle. So the exhaust gas out of the combustion chamber is having a higher temperature in the middle than at the root and at the tip. So something like this. And so we are creating a certain temperature profile or certain pattern factor, okay? There will be also a pattern factor in the azimuthal direction. I will not discuss that here, okay? And that's why we need to be very clear about the temperatures, Very often we have said what? Here we have TT2, here we have TT3. It's not at all like this. Not at all like this. Where is TT3 in this profile? This is maybe an average temperature, but there is no place where you will measure the TT3 that we have called as being the inlet temperature of the combustion chamber. Also, so this is in the radial direction, everything except a constant temperature of the exhaust gases, and in the